Greetings, this is Professor Roman. We continue the lectures on linear algebra. When the minimal polynomial of a finite dimensional linear operator splits over the base field, so it can be written this way, we can improve upon the rational canonical form, which certainly could use some improvement in both appearance and theoretical value. So let's suppose that tau has this primary cyclic decomposition, and the elementary divisors then are powers of linear factors. Now we've seen that the rational canonical form matrix is simply a packaging of the elementary divisors into a matrix package, but we can get a more convenient package by choosing a different ordered basis than a rational canonical form basis, which is pieced together from the tau cyclic bases. That may look like a nice basis, but what it does is it crams all of the complexity at the end when we try to compute, here's the tau cyclic basis, when we try to see what happens when we apply tau to the last basis vector, tau to the EV, we get some unpleasantness, and that's where the last column of the companion matrix comes from. True, it is the minimal polynomial and the characteristic polynomial, that's nice, but so we can find it easily if we know the characteristic polynomial, but the geometry of the matrix is not that nice, with that last column generally being full of non-zero elements. But we can trade in the companion matrix, the matrices of the rational canonical form, for much nicer looking matrices by choosing a different basis. In place of the tau cyclic basis for a cyclic submodule, which as I've shown here, we choose this basis, v, and instead of v, xv up to x to the e minus 1v, v x minus lambda I v up to quantity x minus lambda I to the power e minus 1v. And you'll see what happens here. This is the operator version where I've replaced x by tau. I'm going to leave the proof that this is actually a basis for you. You can certainly rely on the fact that the tau cyclic basis is a basis. Now the vectors in this ordered basis are often written in reverse order, which I'm going to do because I want an upper triangular matrix on the blocks rather than lower triangular. But it's split, I think. Some authors go for the lower triangular, so they wouldn't reverse the order, but I'm going to do that. And so I'm going to write this as script C sub ij, and for simplicity, since these are getting a little complicated, I'll say these are W e minus 1 through W1. Notice that the indices are going down. Okay. Now, to see how tau behaves on this basis, if you look at these vectors, oh, sorry about that, it makes sense probably to try to see first how tau minus lambda I behaves, because that's just going to kick one of these to the next one. Okay. So when you reverse it, it's going to kick one of these to the next one in this list or the previous one in this list. So let's take a look at that. For the first basis vector, which is WE minus 1, so it's almost the full power here. tau minus lambda I to the e minus 1v. When you hit this with tau minus lambda I, you're going to get tau minus lambda I to the ev, and that's 0 because this is the minimal, this annihilates all vectors, because x minus lambda I to the e is the minimal polynomial. For the other basis vectors, wk gets into wk plus 1. So this is the previous vector in the list because I've reversed the order, so the indices go down, which means that a bigger index was earlier, appears earlier in the list. Okay. And now it's easy to see what tau does to the Jordan basis vectors. This I call the Jordan basis. I'm sorry, I may not have said that. This equation tells you that WE minus 1, the first basis in the Jordan basis, because I've reversed them again, this is actually an eigenvector for tau with respect to lambda I. So we have this. And then this equation tells us that tau applied to WK is tau minus lambda I applied to WK plus lambda I times WK, so it's this. So WK gets into the previous vector plus lambda times itself. Therefore, the matrix of tau restricted to this cyclic submodule with respect to the Jordan basis looks like this. Okay. The first basis vector goes to lambda I times itself. It's an eigenvector. The second basis vector goes to the previous basis vector. That's why there's a 1 here in the row above, times plus lambda I times itself. So the 1s give you the previous vector, and the lambdas just give you the product. So I guess I forgot this is to put an I here, lambda I. Okay, and that is much more attractive than a companion matrix. It doesn't shove all the complexity to the last column. It spreads it out more or less evenly. If I hadn't reversed the order of the bases in the Jordan basis, the 1s would simply be on the sub-diagonal rather than the super-diagonal. So it's just a matter of taste. So we can piece these Jordan bases together to get a Jordan basis for the entire operator module. And note that since the Jordan block and the corresponding companion matrix from, let's see, there's the Jordan block, that's this one, and the corresponding companion matrix, which you would get by taking x minus lambda I to the ei, multiplying it out and sticking the negative coefficients along this column, right? So you get the companion matrix instead. Both of those matrices represent the same operator, tau restricted to the same cyclic submodule, but with respect to the two different bases, the Jordan basis here and the tau cyclic basis for the rational canonical form, for the companion matrix. But the point is, they both represent the same operator, therefore they are similar. It's just a different choice of basis, that's all. Well, so since companion matrices are non-derogatory, so are Jordan blocks. And now we can define the Jordan canonical form. In particular, do it for a matrix. For a matrix, A has Jordan canonical form, also called Jordan normal form, over a field F, if A is block diagonal and the blocks are Jordan blocks. So the derivation we have here gives us the Jordan canonical form for any linear operator or matrix. Now, if A and B are similar complex matrices, then they have the same multi-set of elementary divisors, and they're linear powers of linear polynomials, and so they have the same Jordan forms. And conversely, if A and B have the same Jordan form, then they're both similar to that Jordan form and therefore similar to each other, and so Jordan form is indeed a canonical form. In summary, if the minimal polynomial of an operator factors like this, then the matrix representation of tau with respect to a Jordan basis has this Jordan canonical form. Each of these is a Jordan block. So it's just copies of the eigenvalue on the main diagonal and ones above it. And that may get repeated any number of times in the next eigenvalue and so on. When the base field is the complex field, then the Jordan form is a canonical form. You can't say it's a canonical form in the real case because not all minimal polynomials will split. And any operator, real or complex, whose minimal polynomial splits admits the Jordan form. But you can't say it's a canonical form for similarity of real matrices because not all real matrices have a Jordan canonical form. Note also that the diagonal elements of the Jordan form are precisely the eigenvalues of tau, each appearing a number of times equal to its algebraic multiplicity. It's also the case that the number of blocks is the geometric multiplicity, just as it was for the rational canonical form. Example, here is a, let's say we have a matrix 8 by 8, and these are the elementary divisors. These are the Jordan blocks. And so the Jordan form looks like this. I didn't fill in the rest of the zeros because it's a lot easier to see what the form of the matrix is when I just leave the zeros out. The rational canonical form looks like this. Excuse me. So if you want to compare the two, you get them both in camera at the same time, maybe. There we go. See, this has a couple of nasty columns here. This is all sort of evenly distributed, a much more appealing appearance for whatever that's worth. Theorem, let J be a Jordan canonical form for a matrix. Now again, this isn't unique because we can reorder the blocks on the diagonal. The algebraic multiplicity of each eigenvalue is the sum of the sizes of the Jordan blocks. I already mentioned that. The geometric multiplicity is the number of Jordan blocks. And a matrix A is non-derogatory if and only if its Jordan form has exactly one Jordan block for each eigenvalue. Now, what about computing Jordan canonical forms? You can also compute the invariant factor version of rational canonical forms without having to factor. You can't do that for the elementary divisor version. And I do have something in the book on that, which I skipped over. It would be attached probably to the previous lecture. I gave an example of how to do it. So I'm going to leave it for you to look at that if you're interested and if you have the book. I don't want to cover it in the lecture. But I do want to talk about computing Jordan canonical forms. So let's assume then that we can find the eigenvalues of a matrix, and that's a critical assumption. So we can get the factorization of the minimal polynomial. Then we can compute the Jordan canonical form as follows. It has to do with looking at raising certain matrices to powers and looking at their null space. This can be a little bit testy, this discussion. I could have given you an example first, but I wanted to just do this in its full generality as a sort of final parting gesture. Call it the final exam, call it the final challenge. So I'm going to go through this, and it may be necessary for you to review it a few times. Frankly, I just rewrote it just before this lecture because I wasn't completely happy with the explanation I had given. Let's see if this is any better, if it's any clearer. It was a notational problem and thinks it was bad. So here's what we do. In this Jordan form, by the way, I changed one of the symbols here because I wanted to use K for something else, so I wrote L instead. So just to take note of the fact that the number of Jordan blocks associated to a given eigenvalue, or linear factor, base factor, is L sub I, okay, associated with lambda I. Okay. Now, to see what's going on, let's fix an eigenvalue, lambda sub r, and consider this matrix. So I've taken the identity matrix, placed lambda r's on all the entries on the diagonal, and subtract the Jordan form. So the blocks, you do the same thing with each block. You take lambda r times the appropriate size identity, subtract the Jordan block. And already the notation is getting a real nasty, so I'm going to let d sub ij be what you get by taking the ijth Jordan block, so one of these blocks, oops, that's the rational canonical form, one of these blocks, one of these blocks, and just take lambda r minus that block. So you get new blocks and use the same lambda r all the way through. Okay. Let's see, did I go too far here? Okay, so that's what a block looks like then. Okay. With these new blocks d sub ij. And the full matrix, then lambda r minus j, is its diagonal blocks are now these blocks. Now, let's consider what happens to the nullity, the dimension of the null space, of a single one of these blocks when we raise it to various powers. Dij, when I is different from r, this lambda didn't print out very well. I just changed the printer driver. I went to Windows 10, which is a disaster, and the printer wasn't printing. It was print one page at a time and then stop. And I upgraded the driver, and I hope this isn't a recurring consequence of that. I haven't seen this too much before. In any case, when I and r are different, we've got non-zero entries on the main diagonal, non-zero entries on the super diagonal, zeros everywhere else. This has full rank. Just look at the columns. They're linearly independent. Therefore, it has nullity 0. And it doesn't matter whether you raise it to powers or not. This is an invertible matrix. You raise it to any power you want, it's still invertible, will still have full rank, will still have nullity 0. So if I is different from r, then this block, Dij, its nullity is 0, and all the powers have nullity 0. But if I equals r, then we get a block that looks like this. The whole idea of this lambda r minus j is to kill some of the diagonal entries. And they're the ones that are in these blocks, where the blocks associated with lambda sub r, the same eigenvalue. Okay. So now the nullity of this guy is 1, because the rank is 1 less than the dimension. All the columns except the first one are independent. As we raise this to higher powers, it pushes the super diagonal in this direction. So if we square this, the nullity jumps up by 1. Qubit continues to jump till we get all the way to raising this to the power equal to the size of the matrix, and we're going to get the 0 matrix, which has full nullity. And after that, of course, we're still going to be the 0 matrix, still have full nullity. So the nullity of these matrices, these matrix powers, is 0 when I is different from r, and it's equal to the exponent when I equals r until you reach the full size. The power, the exponent, is the full size of the matrix, and at that point the nullity becomes the dimension of the size of the matrix, and it can't get any bigger than that. Okay. So it kind of cuts off here as you raise to higher powers. It becomes constant. Now, in view of the block diagonal nature of this matrix, when we raise it to a power, it's just done by raising each block to a power, which is why we went through this. And so the nullity of this power, which I'll denote by d sub rk, is simply the sum of the nullities of each of these diagonal blocks. That's probably easier to see if you think in terms of the rank. The rank of this matrix is the sum of the ranks of these blocks, because they don't have any interaction with each other. So if we've got some independent columns here and some independent columns from the next diagonal block, all those columns put together are still independent. So the ranks work that way, therefore the nullities do also. But in view of this information here, we don't need to sum the nullities for these blocks, because that's 0. So we only need to sum the nullities for the blocks associated with lambda sub r. that one particular eigenvalue we've picked out. So drk, this nullity, is the sum from 1 to L sub r, that's the number of blocks, Jordan blocks, or these D blocks, it's the same number, and you add up their nullities. Now, that's the consequence of the first equation here, but there's this equation too, which we can take into account. So what we want to do for our drk, we have this sum, it's right here. We're going to split it into two parts. We're going to sum, this is summed over j, we're going to sum over the j's for which the size of the block is bigger than or equal to k. That's going to correspond to this first possibility, and also the sum for where the size of the block is less than k. So, oh, I'm sorry, that's this one, isn't it? Okay. And in fact, yeah, okay, let me say that again. This is k less than or equal to ERJ, which is the first one, and this is k greater than ERJ, which is the second one. So they do line up. And now the nullities can be replaced by either k or ERJ. And so I did that here. Okay. Well, what to do now when things look a little complex? Invent some notation to try to simplify it. So anyway, here's the notation. Little b sub k is the number of diagonal blocks for which the size of the block is less than k. So that would correspond to the second one. And b greater than or equal to k is the number of diagonal blocks for which the size satisfies this inequality. So that will correspond to the first summation here. So what we get then from the previous equation is that drk, this nullity, is equal, these are the two sums we had before, but I've now replaced the summands by k and ERJ. And we get, oh, okay, I already did that, it's right here, k and ERJ. Okay, so now, this first sum is k is fixed. Remember, we're summing on j. So k is fixed. How many of these terms are there? B greater than or equal to k. So this is k times the number of terms. This one is a little nastier, but what I can do is group some of the terms in this sum based on the actual size. This says that the size is less than k, so it can range from 1 to k minus 1. And for a given size, s, we take that size and multiply it by the number of terms, okay, which is b's, okay, that b sub s, okay. I changed the notation a little bit and forgot to change it throughout. I had originally wrote this as b equal k for emphasis and comparison with this one. And I thought, well, that's not that important. I can drop the equal sign here as long as I keep the greater than or equal sign there. But I forgot to drop the equal sign. So it's 4 o'clock in the morning here, actually. So anyway, so I'm going to go back, I guess, to B sub equal S. So I don't want to reprint this and start the lecture again just for something as simple as that. So what to do with this expression now? Okay. Well, the latter sum is still kind of a mess. When k equals 1, it goes away. And so dr1 is just the first term here, and that will be 1 times b greater than or equal to 1. So b greater than or equal to 1. The number of blocks of size bigger than or equal to 1. When k is bigger than 1, this sum isn't going to go away, but there's a nice little technique for dealing with that, and that is we subtract 2 of these consecutive ones, and that will kill, well, it will give us a single term rather than a difference of 2 sums. So here's what it looks like. drk minus 1, I've just written the 2 expressions here twice, once for k minus 1, reorganize. I'll let you go through this. It's not too bad if if you're calm and don't lose your head. And lo and behold, it all kind of really simplifies, and it comes down to b sub greater than or equal to k. It's very nice. So it matches this one. So b sub greater than or equal to k, the number of blocks of size at least k, is the difference between these 2 d's. It's the difference between these 2 nullities. This may not look like much of a simplification of matters, but remember that the nullity is something of a matrix, something you can easily compute. It's just a matter of solving a homogeneous system of equations. So that can be done on the computer, for example. Now, since b sub equal k, here I did drop the equal sign. I wasn't very consistent. I'm seldom consistent this early in the morning. B sub k is the difference between b sub greater than or equal to k and b sub greater than or equal to k plus 1. We get a formula for b sub k. And it looks like this. B sub k is twice this nullity minus that nullity. We're taking the nullities of powers of this matrix. Something that may be bugging you here, and it probably should be, is, well, all this discussion uses the Jordan form, and that's what we're trying to find in the first place. So I saved the important point here for last because I wanted you to be worried about that. I wanted you to notice that. The fact is that the original matrix A is similar to the Jordan matrix. So let's say here's a similarity. And so the nullity of these matrices involving J is the nullity of this. This pulls out, same as the nullity of this. So our formula that is of use, this was of absolutely no use because it's trying to find the Jordan form using the Jordan form. But now we see that this is what the formula looks like. The number of Jordan blocks of size k, k by k, is equal to this nullity, this expression involving nullities. So, in theory and often in practice, we can deal with this, So let's look at a simple example. Here's a matrix. Here is its characteristic polynomial. Okay? And this matrix only has one eigenvalue. so I have to do it with one block. It would be exactly the same with each eigenvalue. So this really is general enough to give a good example. So what we do is we have to compute the powers of this matrix lambda 1 I minus A. First power this is the matrix if we raise this to any power bigger than or equal to 2, we get 0. So the nullity of this matrix works out to be 2. There's only one independent column here, really, or row. Be easier to look at the rows. And the nullities of higher powers are all 3, and so the number of blocks of size 1 by 1 is, you use the formula here, and you get 1 block of size 1 by 1, and you get 1 block of size 2 by 2, and so that's the Jordan form. This one is simple enough to deal with in other ways, but it shows you that all we're doing is computing nullities and plugging into that formula, and we get the Jordan form. All right, now, that finishes chapter 9 of the book, and it finishes the proper portion of the course, comprehensive introduction to linear algebra. I think it's been comprehensive. I've covered a lot of ground. We've talked about numerous topics that are generally not covered in a standard undergraduate course. Some of these might be covered more at places like MIT and Harvard and so on, although I taught linear algebra at MIT and I didn't cover it. So if you stuck with the course, and if you spent some time and energy trying to absorb the ideas, you've learned a great deal of linear algebra, equivalent to a good portion of graduate linear algebra. So that you can be proud of what you've done. There is more to the book. There are topics chapters, and let me show you what they are. Even in elementary, freshman, sophomore linear algebra, I mention anyway, without any sort of proof, that while the row echelon form of a matrix is not by any means unique, the reduced row echelon form is unique. The proof is well beyond the reach of students at that level, but does not seem to appear at least not in my experience, even in upper division linear algebra courses. So I give a proof here. We haven't spent much time with determinants. In freshman, sophomore linear algebra, you get a dose of determinants and their properties, such as the determinant of the product is product of the determinants and so on. But the definition of determinant is given in terms of cofactor expansions, and one says that you can expand along any row or any column and you'll get the same result, but proofs are missing. The fact is that there are 3 definitions of the determinant in common usage. There is a permutation definition, which is not discussed, certainly not in the freshman sophomore course, but I don't think it's discussed too much in upper division courses either. It may be mentioned, but not with any detail. There's a multilinear form definition of the determinant, which I'm fairly certain is not discussed generally in undergraduate courses. And then, of course, there's the cofactor definition. So what I do in this chapter is give you the three definitions and show how they are in fact equivalent. So this is a very important chapter for those keenly interested in how determinants work. The next chapter is on the Ldu factorization of a matrix. There are some very important matrix factorizations. The QR factorization we discussed in the text. This factorization, LDU, would be discussed in undergraduate upper division linear algebra courses that are oriented towards applications, not towards theory. And maybe in some others. I mean, I don't want to speak too generally because I'm only acquainted these days with 3 or 4 upper division linear algebra books. So anyway, this is one of the 3 key, most important factorizations of matrices. The polar and singular value decomposition, this is the third important decomposition. It gives rise to, or factorization if you want, gives rise to something called the Moore-Penrose generalized inverse. It's a generalization of the notion of inverse that applies to non-invertible matrices. The next topic's chapters on tensor products. I get a lot of questions in my classes, what's a tensor product? And so I have endeavored to give a gentle explanation of tensor products and how they work. The final topics chapter I called Modules, the Vector Space Appreciation chapter. As I discussed very briefly at the beginning of this lecture series, or maybe actually, the beginning of this material on operator modules, that modules in general are much less well behaved than vector spaces. There are modules that have no bases. There are modules that have bases of all sizes. There are other issues. You can multiply a non-zero module element, non-zero vector, by a non-zero scalar and end up with 0. All sorts of things can happen. And so I go into a little bit, not much, it's only, about 6 pages, a discussion of modules in general, and issues like linear independence, torsion elements, which are the ones I've just described, and free modules, which are modules that do have a basis. And just to give a contrast and help you appreciate how nice vector spaces are to study relative to the study of modules. Well, I've decided not to do lectures on these topics chapters. So if you have the book, of course, you can read them. If you don't, then you'll miss out on this part, but you will still have that fundamental core knowledge, quite extensive knowledge of linear algebra. And so it only remains now to thank you if you've managed to persevere to this point in the lecture series. And I will probably take a bit of a break. You may have noticed I have done so recently for various personal reasons. We had some issues. I'm going to take a little break, and I'm working now on a program to organize and play classical music on the computer. I have a collection of some almost 7,000 individual tracks of classical music, and I've been spending time organizing that in a database and writing a .NET program for the Windows computer for playing the music. And I'm finishing that up fairly soon, and I'll return to the lecture series. The next course in this 3-part or 4-part series is group theory. So I hope to return to that in the not too distant future. Again, thank you for watching my videos.